Welcome to AP Calculus AB. Hi, Fagan.
Okay. All right, hopefully this isn't going to confuse you with what you have on the quiz.
Now I know it's going to confuse me.
It's not going to confuse you.
Now I see your trick.
Oh, no. Because it's more on limits, because continuity has to do with limits also. So hopefully it'll help you. Okay, so you talked a little bit last year about continuity or continuous functions. Yes? Okay, so an example of a graph that's continuous is one that you don't lift your pencil. Right, so like a polynomial is a continuous function. Now, we get into kind of a weird, when it comes to continuous functions, the reason they're continuous has to do with the domain, okay? So an example, and I have this coming up later on, but, oops, y equals 1 over x. You know what that graph looks like?
Yeah.
1 over x? Okay. So that's actually a continuous function.
Because it keeps going.
It has to do with, and we'll get there, but y equals 1 over x is continuous from negative infinity to 0 and 0 to infinity. It's continuous on its domain. So the domain excludes 0, right? Now, we don't worry about in calculus calling something a continuous function versus a discontinuous function. What you'll find are most functions that we work with are continuous. And the weird part about that is they actually have points of discontinuity. Weird, I know. So this is a continuous function with a discontinuity at 0. And it all has to do with how it's defined. It's defined according to its domain. Now 0 is not in its domain.
But with that logic, isn't every function a continuous function?
Okay, so yes, except for like piecewise functions. Yeah. Also, the step function that we talked, the greatest integer function. But otherwise, yeah, pretty much everything, even with holes in the graph, those are continuous functions. Don't worry about that. I'm not going to ask you to say if this is a continuous function or not. I'm going to ask you, is it continuous at an actual point? Okay, and that's what the AP exam is concerned about. So how do we know if it's continuous? Well, the limit from the left and the right, which is basically your limit here, is equal to the actual point. Right? So the left, the right, and the point is actually filled in. Those are all the same. Then we have continuity at a point. Now, sometimes you just have an endpoint. So, for example, if this one's at a left endpoint, so let's say I have a graph, and it's like this. I know it's continuous. Oh, at a left endpoint means that we are approaching that value from the right, and the actual value is filled in. That's continuous at a left endpoint, and then a right endpoint would just be approaching, be the opposite. Okay. We'll go through examples. So I'm just kind of, okay, so depending on if it's an endpoint, we just look from one direction, but at an interior point, we want to look at from the left, from the right, and at the point. Now, these are the types of discontinuities that you need to know. And I'm actually going to say just the first 3. So you need to know. Oscillating is good to know, but it just never shows up. Removable discontinuity, jump discontinuity, and infinite. Those are the 3 that you need to know. Now, how do we know if it's a removable discontinuity? So, Brittany, what do you have? Hole in the graph. So the way it would be described with limits would be, let's say, the limit as x approaches 1 from the left is equal, actually let me put f of x in here. That's when the limit from the left and the right are equal to each other, but these are not equal to f of 1. Or sorry, I put in 1. I meant to put 0. Let me read. 0 from the left, 0 from the right, and f of 0 So these two are equal, but the actual value is not. Okay. Jump discontinuity. This is when the limit from the left and the limit from the right are not equal to each other. So this is, we could see the limit as h approaches 0 from the left is not equal to the limit from the right. That's a jump discontinuity. It's as if you're working left to right and it jumps to a different y value. So in this case, I don't care what the actual point is. Doesn't matter where it is. Doesn't matter if one of the points are colored in or if it's in a different location altogether. All I have to consider are the left and the right hand limits. And then in infinite discontinuity, this is when you have a vertical asymptote. So this is when your left or your right goes to infinity. Good? And we want to be able to tell the difference between the three. Can you just see them? Yes, if you graph them. Yeah. Okay. So we want to find intervals of continuity and the points of discontinuity of the function, and then identify each type of discontinuity. So if it's a jump, removable, or an infinite, and sometimes you can have more than one in a function. Okay. So this one, what do we have? What do we want to do first? Good. So let's factor it. And it factors into x minus 2, x minus 1. Okay. Right? Okay. Now, does anything cancel? No.
Not yet.
Okay, since when you cancel, what does that make? That makes a removable, right? A hole in the graph. So I know these two have to be, right, those are vertical asymptotes. Okay, so I know it's continuous on negative, so from negative infinity to 1, and then 1 to 2, and then 2 to infinity. Just make sure when you write an interval notation, right, everything goes in order. Now, discontinuities. We have discontinuities at x equals 1 and x equals 2, and they are infinite. Okay with that? Now, if we had one was removable, one was infinite, you would just have to write down which one switch. Okay, how about, any questions on that one? Okay, how about B? What does this graph look like? It's a V shape, right? Absolute, yes, absolute value.
Yeah.
V. So, tell me, continuous, discontinuous, what do we have? It's continuous everywhere, right? So, it's continuous from negative infinity to infinity. And if you write negative infinity to infinity, you don't have to go any further. You don't have to write no discontinuities. It's implied. That's all it is. All right, how about the next one? Notice, what's that? Don't waste your time. ln of x minus 1. What do you say?
Put these in our calculator.
Well, you can
See the graph?
0, which is 1.
Okay, so let's think about this.
We're allowed to.
What's ln?
ln of 0.
We're learning how to do it without a
Oh, okay.
Have I looked at my calculator? No, we're good. We don't need
Okay.
it. We don't need a calculator.
ln negative numbers.
Okay, ln, we talked a little bit about natural logs. So what the domain for natural logs or logarithms, you can't plug in anything less than, or right, you can't put 0 in either. There's a vertical asymptote. Now, if it's x minus 1, then our vertical asymptote is here at x equals 1, and it looks, again, very rough sketch, but something like that. Now, I can graph this without lifting, so this is an example. I can graph this without lifting my pencil. Are there any holes in the graph? Okay, now, that asymptote, is that separating another part of the graph? No, there's nothing over here, is there? So we're going to say it's continuous from 1 to infinity, and this one has no discontinuities. So be careful here. Even though there's a vertical asymptote, it's not, that's that's not like separating. It's not like a rational function where I have part of the graph over here and part of the graph here. It's just the graph starts from here. So this has no discontinuities. Does that make sense? Okay, how about D? E to the 2 over x. So you might not know what this looks like, but exponential functions, usually you can plug anything in, right? But we have this 2 over x business. Yeah, so it doesn't matter that the exponent has a variable in the bottom, that you still can't have 0 in the denominator.
There's a hole. That's 0.
Not a whole. There's an asymptote. And this, if you weren't sure, this, you should recognize anytime you have something in fraction form and you have a variable in the denominator, that's going to mess with our domain and our continuity, okay? Now, this is a vertical asymptote. There's a vertical asymptote at 0, right? So I know it's going to be continuous where? Right, negative infinity to 0, 0 to infinity. If you aren't sure, you can graph this, but there is an infinite discontinuity at x equals 0. Question? Yes.
For C,
Uh-huh.
like just that one there, that equation general, can you distribute the ln so it's
Oh, no. No.
But then what's the
No, don't distribute functions. Natural log, sine, cosine, these things are functions. We can't distribute them. What you're thinking of is, what you're thinking of,
You're thinking of division. Like
So,
dividing.
like if I have an ln of x minus an ln of 1,
okay, yeah.
that's equal to ln of x over 1, right?
Yeah.
I'll forget we talked about that. Don't ask me if we can distribute logs. Okay, it's okay. You can ask me. I won't make you feel bad. Possibly.
I think you already did.
Yeah, it would be too late on that one.
Sorry.
That I just
Oh.
Okay. It's okay. Everybody always asks. I know. Example 2. So we have a piecewise function. So how about we graph it? What's it look like?
line and dot and
Yeah, so what do we have? We have a negative x squared plus 1. And, right, so at negative 1, if I were to plug in negative 1, I actually get 0, and it's filled in. And then once we get to 0, it's actually, so it looks like that. It's just a little part of negative x squared plus 1. Now that's an open circle right now, but when I get to the next part of my piecewise function, now I'm actually going to color it in, right? Because it's x is greater than or equal to x. And now it's filled in nicely, I think. It's not open, is it? And then we go up to 2. It's harsh. So here, oops, I made a mistake. Goodness. Yeah, it's up here. Goes up here. And this is an open circle. And then at x equals 2, we get 4, so that's going to be colored in. And then x greater than 2 is negative x. So basically down here is going to be an open circle, and it's going to go that way. Good with that?
What is this sort of negative 2? Oh, right. Yeah, I know.
Yes? We're clear on that? Okay. Now we want to ask some questions about this. So, does f of negative 1 exist? Yeah, of course. There's a colored in circle. Yes? Yes? Okay, how about 1 from the, approaching 1 from the right? Careful, yeah. That's right here. This is part of this line, so that's yes.
wait, it's from
You
the
mean from the
Or
left?
it's from the left, sorry. From the left. Yes.
I would have gotten every question wrong if you hadn't. I would have, and every limit messed it up.
All right, how about the limit as x approaches 2 from the right? Does that equal f of 2?
No.
So the limit from the right,
4.
no, doesn't match up.
Oh yeah, limit.
Is f continuous at 0?
Sure.
Yeah, so
Yeah.
it started out with an open circle, but when we did that next part, we were able to fill it in. If this was just less than, then we would have that as an open circle, right?
And then it would be no.
And then it would be no. Okay. Example 3. So similar problem, but now we want to find each point of discontinuity, and then which ones are removable or not removable, and let's just state reasons. So I'll give you guys a minute to go ahead and graph that. We actually don't have too much more, so we should have plenty of time for that.
So the way here, you know, how to do this.
I make little if you're having trouble, I make like little tables. So if this is, so like this first part is x is less than 2. So if I were to plug in 2, I just keep in mind that would be an open circle there. So 3 minus 2 is 1. Maybe I can plug in 1. I get 2. So like at 2, 1, I have an open circle. So it looks like that. And then I have a point at 2, 2. And then this one is x greater than 2. So if I were able to plug in the 2, it would be an open circle there. But it ends up being the same open circle as this, right?
Yeah.
And then plug in 3 or maybe 4 over. Okay, so did you get like almost, it looks like an absolute value, but this one side has a smaller slope, like that. Okay, but we never filled in that circle, right? Because this is where x was equal to 2. Okay, so find each point of discontinuity. There's 1. And whenever it asks for a point of discontinuity, we only need to say the x value. Because a place of discontinuity could be a vertical asymptote. If you have a jump discontinuity, right, you don't need the y value. Now you could have a removable discontinuity and you could say, oh yeah, well there's a removable. But all I need and all the AP exam will ever ask for is an x value. Okay? And so x equals 2. And which are removable. The reason I have it phrased this way is this is how your homework looks. So x equals 2 is removable. Now, what's the reason? Because the limit as we approach 2 from the left was what? That was, well, it's equal to 1 from the left. Right? The limit from the right is 1, but f of 1 is equal to, did I say that? Sorry, f of 2. F of 2 is equal to 4. That's the reason. So the left and the right are good. Those match. Oh, goodness. I'm really, seriously. So the left and the right, those match up, we're good, but f of 2 is not the same. So here's what I was saying in the beginning, and I don't want you to get too hung up on it. I'm happy to have discussions later. I always get these arguments students want to have with me about this idea that this is a continuous function. I promise you it is a continuous function, okay? And because here's how a continuous function is described. It's got to be continuous at every point of its domain. So if there's a number that's not in its domain, then it's like we don't even consider it. So we think of this as like each part. So yeah, this is all continuous. This is all continuous. The only place it's not continuous is at 0. 0 is not in its domain, so I don't care. That's how. If you go higher into mathematics world, then you might encounter more of this. But
Hopefully you won't have to.
for us, in this class, you just need to be able to describe the intervals where it's continuous and then be able to identify the places where it's discontinuous and what reason, okay? Now, these are just more limits. Okay. So if you have like two continuous functions, an example, right? So if I have, is x squared a continuous function? Yeah. Is sine x a continuous function? Yes. So I know x squared plus sine x, that function is continuous. So if each part is continuous, then the whole thing is continuous. And that's going to stay true for subtraction and also multiplication. So if I said x squared times sine x, that's also continuous.
So if both are continuous, then continuous.
Exactly. Now notice, and also division, multiplication, constant multiples, and division. So I could take any two functions, you know, as long as the denominator is not equal to 0, and if I divide them, then it's continuous. Also, composition of functions. Compositions like f of g of x, right? Fog. Yeah. So if you, what?
I was always a golf man.
Oh, gosh.
You're wrong.
We don't actually use the little circle too much in calculus. You'll usually see just the extra set of parentheses. That's how it would be.
Why
Save
even
time.
show us that little circle?
Because it shows up. I mean,
Why
it's
would
good
you
to know. I don't know. Does it show up on SAT at all? Maybe.
I think so. Yeah.
That's, I mean,
ACT it does.
we try to, that's what I was going to say. Usually the books will have whatever testing is out there, so they want to make sure that they cover everything.
Our curriculum revolves around tests instead of the other way around.
Yeah.
We're not gonna fix
We're not
the
gonna go into
education
that.
system, guys. You guys
So-
are almost done. Just
So here's the thing. If f is continuous and g is continuous, then g of f is continuous, or the other way around also. Okay? So here,
Oh, we just did that.
we want to explain why the given function is continuous. My parentheses aren't showing up, but so first of all, we have to figure out what is the composition here. So we want to be able to explain this. So let's say, maybe I'll say h of x is what's in, when we think of composition, sometimes it's helpful to think what's on the outside and what's on the inside. What's on the, let's pick the inside. I know my parentheses aren't there, but just on your, just x squared plus 1. Aren't there parentheses around this
Oh,
Yes.
yeah.
in your thing?
Yeah, sorry.
Okay, so I'm going to say h of x is going to be the inside function, x squared plus 1, and maybe I'll call g of x. Now I can't just call it sine and not have something, just for the same reason why I said you can't distribute. So it's sine of x. We'll use the same variable. Okay, now I can redefine, so both of these, right, this is continuous, right? And we know that this is continuous. So therefore, and we have, this will be g of h of x
what is that?
is continuous.
Therefore,
Okay, so I'm going to teach you throughout the year a couple of little shortcut stuff because
Don't waste
we
your
in the
time.
math world like to abbreviate whenever possible.
can we do the
So
also?
this-
Except for when you're showing your work.
Well, yeah, but sometimes there's some supporting work that must be shown. What?
Just fun facts.
What was the fun fact? Oh.
Check the rest.
I remember when we were doing geometry and you taught us that, and I used to use it for the reflection, like for the proofs all the time. It's my favorite.
I don't think I got one proof right. In all the geometry.
Reflection.
Well, it's a good thing we don't do geometry proofs in calculus.
Mr. Evil.
Okay.
I took geometry.
I passed geometry because math was introduced in semester 2.
Okay, last thing, and then we'll get to the quiz. So, I know, I didn't forget. Okay, intermediate value theorem. Did I talk about this a little? No, okay. I'm trying to like remember each, having so many different calculus, it's hard to know. Because I was reviewing this with the BC class. So here's what the intermediate value theorem says. And I like to just think of this as you have, let's say you have a graph, right? And let's say you have a point down here and a point up here. So let's say this is my A, f of A, whatever that point is, and B, f of B. Right? I got 2 points. One's below the x-axis, one's above the x-axis. Intermediate value theorem says if you have a continuous function, then it's got to cross the x-axis at some point, right? So I don't care what happens in between. Could pass one time, several times, but it can't jump over the x-axis. That's all the intermediate value theorem is saying. If you have a point here and a point up here, it's got to take on all the values in between. It can't jump over a value. So you might encounter this on the free response at some point down the road, and they'll just, maybe you come out, like maybe somebody was driving at 30 miles per hour, and then they were driving 50 miles per hour. So at some point, were they driving 45 miles per hour? Yes. Why? Intermediate value theorem.
Can't you technically go from 44 to 46? So like,
Not if it's continuous function.
Wait, I don't get that's not possible.
You can't jump over, and with your speedometer in your car, your parents' car, or whatever,
You can't jump
Right?
over a value.
you can't jump from 45 miles per hour to 40.
No, but your
I
speedometer
know.
can show.
It just doesn't
But
show
it
it.
doesn't, yeah.
It doesn't show it.
Is it like a digital?
Yeah. Because speedometers do average.
No, mine-
But you understand that you can't actually
Yeah.
skip over 46 miles per hour or something like
I
that.
never liked 46 miles per hour.
Okay.
In order to get from one
I can use the measuring
Okay,
power.
you get the idea, right? Right, you get that explanation. Okay, so we want to make this piecewise function continuous, okay? So if it's a piecewise function, we want to look at specifically, the domain part. So everything up to 2 is going to be continuous here, because that's the equation of a line. This is also the equation of a line, ax plus 1. So I just need to make sure that those two are equal to each other, right? So I need to make sure the limit as x approaches 2 from the left, right? I want to make that equal to the limit from the right, as well as f of 2, which happens to be the same as the limit from the left. Okay, so I'm not really going to consider this. I'm just going to look at these two parts. So the limit from the left is going to be what? 2 times 2 plus 3. And I want to make that equal to, from the right, 2x plus 1.
So it has equal.
It's that simple. Oh, 2a plus 1. Because of the domain. That's the only point in question. Up until that,
Will it
everything's
always be
continuous.
like 2 and 2, or will it ever be like a 2?
Yeah, I'm always going to give you something that's like the same value. So I have 7. So a equals 3. That's all. Okay, so if you didn't get me your homework, did everybody put it here?
Oh, I didn't.
Anybody else still?
I had some more questions. Alex is really like. It's not
That's
hard,
after
right?
lunch, you said? It should be fine.
Okay, well, I need to.
I think I'm gonna keep finishing the.
So I'll come with that.
So, yes, there are 10 questions. Yeah, see, I know it. I was pretty sure. Sometimes I revise stuff from year to year, so I always forget. Staple there. Oh, no, don't staple Hebrew. Okay, so have your calculators out, but just have them aside for the first part so you're not tempted. Wait.
These two I had questions on. Could I?
Well,
see,
you
like,
can ask me after,
I'll ask you
or,
after, and then
okay. Or you can turn it in and just me not reading those.
In this case, if we're all, I think this assignment right from
Oh yeah, it's assignments 2 and 3, so I just have you staple 2 and then 3 at the bottom.
There's no calculator.
Isn't the odds
Okay, who got quiz A? Quiz A. Quiz B.
Oh, dude, can I get these so I can cheat off Josh?
What's the period?
B.
Guys, it's the 1st of September.
Haha, I got B. I can cheat off Josh. Gotcha.
Okay, so
Oh no.
Oh, yes.
Oh wait, this is the no calculator part.
no calculator part first. And again, if you have extended and you think you won't have time to finish the other side, then we'll have
Wait, can I do the calculator part first?
if you want.
Oh, we get fractions now.
Well, as long as you didn't really see the